Well, good morning, everyone.
Good morning.
My name is Brian Jarvis. I'm from Eatec Dynamics, and my talk this morning is all about noise and vibration from construction demolition sites. So the objective is to say why noise and vibration is important, how you would go about measuring it, what limits you would set for the maximum noise and vibration that you might disturb neighbours with, and then what you could do to mitigate both noise and vibration should you find those limits are being exceeded. Right, so first of all, why do we need measurement? And there are two stakeholders here. There's the developer, and his requirements are that he wants to work quickly, he wants to use the most efficient equipment, he doesn't want to be stopped by people complaining that he's generating too much disturbance to his neighbours, and he wants to avoid unnecessary expense. So as far as he's concerned, he just wants to get on with the job and not be bothered by noise and vibration at all. Neighbours, on the other hand, don't want to be disturbed. They want a peaceful existence. Quite often you'll find that there's some hostility anyway before work starts if it's a big project. So they are particularly sensitive to being disturbed. They can be very concerned about damage to their property, particularly where vibration is concerned. If they feel vibration, then they assume that the fabric of the property must in some way being damaged, and they want to know how they can complain if they find that they feel disturbed or they believe damage is occurring. And so we need measurements in order to quantify what's going on. How can we be certain that the levels of noise and vibration are going to be acceptable, that we're not putting unnecessary constraints on the developer, but we are at the same time protecting the residents nearby. And there's some British standards which cover the area of noise and vibration, and the best ones by a long way are the two coming under BS 5228, the Code of Practice. And part 1 is all about noise, and part 2 is all about vibrations. And they not only tell you how you go about doing measurements, but they also give you guidelines as to what are fair limits that you should set. It's unreasonable for residents to expect that there will be no increase in noise or no increase in vibration. But at the same time, it can't be excessive to the point where they're being disturbed unnecessarily or too much. Any limits we set really need to be supported by national standards. We can't go in and arbitrarily say, well, we'll set a limit of 90 dB here, and as long as we don't exceed that, no one will complain. Well, they will, and it wouldn't be supported by a national standard. And the local authorities often go to those standards and will say, right, I'm going to impose a limit for this work of a particular level. Obviously, if we're going to set limits, then they've got to be measurable in some way. So we're going to have to put instrumentation in there so that we quantify noise and vibration, and I'll cover that in some detail. And we've got to be realistic that we can't put in instrumentation which is so expensive that it jeopardises the economic viability of the work. So we've got to be pragmatic about what we do here. And as I say, BS 5228 is an excellent code of practice, giving lots of guidelines and help in there. And I've brought some copies with me today, so if you're not familiar with that standard, it's worth having a look at. Now, there's legislation which backs up the noise and vibration exposure of residents, and it's worthwhile just being aware of what that is, because that can have an impact on how you go about measuring noise and vibration. And the overall legislation is covered by common law, and in common law there are clauses which allow citizens who might be affected, to prevent or secure the abatement of a statutory nuisance. That's the terminology that's being used there. And they specifically mention the control of noise and vibration from construction sites. So at the end of the day, if everything breaks down, then citizens have the right under common law to try and get the work stopped under those under common law. But there are some specific bits of legislation which are worth. There's the Environmental Protection Act, which gives the mandatory powers to local authorities to control a noise nuisance. There's the Control of Pollution Act 1974. That's worth being aware of because that specifically covers noise and vibration and gives the powers of the local authorities to control it, and gives you, as representing people developing or involved in construction, an ability to set limits or agree limits in advance of work going on. And I'll mention that in a bit more detail soon. There's the Health and Safety at Work Act 1974. That's about protecting people working on a site. So here we're looking at high levels of noise and how to protect hearing. So as far as noise pollution is concerned, that one shouldn't come into it. You should never be at levels on the boundary where your neighbours need hearing protection. And then there's the Control of Noise at Work Regulations 2005, and that defines the action levels required for hearing protection. Again, it's to do with workers on site and the level of noise that they can be exposed to. The Control of Pollution Act has two sections in it which are worth drawing your attention to. Section 60 is all about the powers that a local authority has to, when they believe that noise is being exceeded or vibrations being exceeded, or when you start a project and you're applying for planning, it allows them to specify equipment used. So if you're generating, let's say, a lot of noise from a site and you've done no liaison with the local authority in advance, and someone makes a complaint and measurements subsequently show that you are over an acceptable limit, the local authority can step in and specify that you use different equipment. They can specify that you work different hours, and they can change working practices. So the local authority has a lot of power if you don't take precautions in advance of carrying out some potentially noisy work. But Section 61 of the same Act is a consent, and this consent, which is often in the form of a long form that you fill in with the local authority, allows you to define what levels you're going to work to, define the equipment you're going to use, the working hours, you agree noise and vibration limits, and providing you keep to what you've agreed to, then the local authority cannot use Section 60 to stop you. So not only is it good practice to plan, if you're going to do some noisy works, to plan what you're going to do in advance and to make sure you're using the right equipment, but if you agree with the local authority within Section 61 consent in advance, it gives you the protection then to ensure that your work won't be stopped by, as long as you obviously keep to your agreement, by people who are complaining. Just like to say a little bit about what is noise, physically what is noise. And noise is a sound. It's a pressure wave in the air that has been initiated by the vibration of some hard surface. So that hard surface might be concrete slab, and you're hitting it with a metal chisel, and the surface vibrates. That causes the air locally to the surface to vibrate, and that transmits through the air and reaches your ears, where it's turned back into a signal and the brain interprets it as noise. Generally, noise is defined as unwanted sound. So sound is the general term for vibrating air pressure, and some sounds are good, like music and speech, and you want to generate those sounds, and some sounds are unwanted, and we tend to term those noise. The pressure waves lose their strength with distance, so the further you are away from the source, the lower the sound. That shouldn't be any surprise. Low frequencies travel a lot further than high frequencies. So if you're generating a low rumble, it might be through some mechanical equipment working, a pump or something like that. That sound travels a lot further than a high-pitched whine, which might be annoying close to, but is easily damped with distance and easily damped with sound attenuation as well. So if you're going to use low-frequency equipment, things which rumble, then be aware that that is going to travel a long way and actually be quite difficult to stop. Because noise is an air pressure, when a microphone measures it in the air, it's in a pressure term, like pascals. But we always think of noise in decibels, and decibels is just a logarithmic way of describing pressure in pascals. And we tend to use decibels as a logarithmic measure because our ears hear in a logarithmic sense, not in a linear sense. So it makes it more useful to describe a noise, air pressure, in decibels rather than pascals. How does noise affect people? Well, unfortunately, it's not uniform. Different people are sensitive to noise in different ways. But in general, we can think of noise depending on how loud it is, what's the maximum pressure that we're generating in the air, how long we're exposed to it, so the duration of the noise, when it occurs, that's, so if we hear a noise at night, we're likely to be more disturbed than we are during the day. The local environment, if we're living in a busy urban environment, we're less likely to be disturbed by noise of a particular level than if you live in a rural environment where things are generally quiet. And tones in noise are also a disturbing feature. So if there's a background noise and there's a single tone in it as well, even though the level might not be excessive, you perceive the tone, and that can be quite disturbing. But the most important factor about noise is that we don't hear equally across the whole frequency range. So down at very low levels, low frequency levels, the ear is not very sensitive. So if we were to have a sound in here of, let's say, 60 dB at 10 hertz, none of us would actually hear it, even though 60 dB is about the level that I'm speaking with at the moment. 65 dB is that level. But at 10 hertz, you really wouldn't hear it. You might feel it, as a vibration, but you wouldn't hear it. Similarly, at 20 kilohertz, we wouldn't hear that either. In the middle, we hear it much more sensitively. Now, a microphone, unfortunately, picks up equally across the whole frequency range. So if we were to just look at levels straight from the microphone, we would get a level which is not representative of how our ear hears that sound. So to compensate for that frequency colouring that the human ear has, we use something called A weighting. So a sound coming in at very low frequencies is attenuated at around 1 kilohertz. It's left untouched. At around 20 kilohertz we start to dip off again. So we take the microphone signal and multiply it by that weighting curve here to end up with a level that is representative of how the human ear hears. And that the general weighting that's used is called A weighting. And so when you see a dB reading given in terms of noise and noise in construction, it will usually have an A written after it, and it's important that measurements are done in dBA, otherwise we can't use the limits that are set in the various standards. So, which is why I've dwelled a little bit on A weighting. Now, what should be measured as well? This is not obvious as to when you're measuring noise, what is it actually we should measure? Should we measure the loudest sound you hear? Should we measure the top 10%, the average over a period of time? All of them have different abilities to produce annoyance. So if there was suddenly an extremely loud sound, but it was a one-off, people could be quite disturbed by that. Similarly, if it was a general buzz in the background, but just continuous, people might be equally disturbed by that. And over the years, various methods of assessing the level of noise when you want to measure it against a limit have been developed. And I've given 3 of the most popular ones here. The first one is called LA max. When sound is mentioned, they usually use the term L. Not quite sure why, maybe it stands for level. The A stands for A weighting, so we talk of sound pressure with the A weighting, and max means it's the highest sound. So in the instrumentation, if you're looking, or if the limits have been set for you for an LA max value, they're looking for the very loudest sound that's been produced in a period of time, say a day. That doesn't help if you've got something more continuous going on, and so another measure that's used here is LA, and XX stands for percentage we put in here, and T represents a time interval. And what that is saying is what is the level of noise that has been exceeded for XX% of the time. So let's say XX was 90. What's the level of sound that's been exceeded for 90% of the time over time period given by T, maybe the working day? And that's often the measure that's used for road traffic noise, to give a measure of the annoyance of road traffic noise. So you'll come across it, but for noise from construction sites, that one is not used except for background noise levels, where XX is generally 10% there to give a background noise level. The one that's most commonly used in the standards for noise from construction sites is LAEQT. LA is the A-weighted sound pressure level. EQ means equivalent, and T over a period of time. And essentially, the T will be either a daytime, 16-hour daytime period or an 8-hour nighttime period. They're generally how T's are used there. Although they don't have to be, they could be 1 hour, they could be 5 minutes. But generally, when the limits are set, they are for a 16-hour day and an 8-hour night. And the LAEQ is the equivalent continuous noise level. So if you were to take all the noise gathered, the peaks, the troughs during the period T, and you do a logarithmic averaging of it to get to the equivalent sound level, that's you would arrive at LAEQT. The instrumentation will do this for you. It's too big a calculation for for you to take individual measurements and try and do all that independently. But sound meters will carry out that averaging process to get an LAEQT. And that's the measure that's most commonly used when looking at limits. Where should noise be measured? That isn't obvious either, because if you were to put a microphone in the middle of a field, perhaps I shouldn't use the term field, it's called a free field measurement, but it has nothing to do with the field. If it's unaffected by reflecting surfaces, then that's called a free field measurement. And it will be a different value that would be measured compared to putting the microphone close to a wall. However, on most building sites, walls are around the boundary. So the standards have been set, assuming that you're going to install the microphone 1 metre away from the nearest sensitive building. And the standards also tell you to place that microphone close to a window or door that is adjacent to where the works are going to take place. Now, in actual fact, the measurements made by that microphone will be about 3 dB higher than if it were unaffected by any facade nearby. But the limits take that into account. And in fact, if you find that there are no facades nearby, and you have to take a free field measurement, unaffected by reflections, then you adjust the limit down by 3 dB accordingly. So, but normal practice is noise levels measured 1 metre in front of the most exposed of any windows and doors in any facade of any eligible building nearby, any sensitive building, the one you want to protect. So that's where you should measure. We discussed what you should measure. Now we've got to set a limit for how much sound you should be exposed to. Now I've put this chart here just to give you a feel for what decibel levels mean. So 0 dB is defined as silence. It's of course not silence, there's still some air pressure there. It's just the threshold of hearing of the most sensitive person. By the time we get to 60 dB, that's normal conversation. I'm probably speaking about 65 dB here, a bit louder. When we get to 85 dB, that's the point where hearing protection should be worn. So if your neighbours are being exposed to 85 dB, then you're really putting too much noise over the boundary. And then you can get up to a rock concert at 120 dB. In my opinion, permanent damage is starting to be occurred at that point, so you should wear hearing protection at a rock concert. Fireworks, 130 dB, and a jackhammer, 140 dB. So the most common limit level that's set is 70 dB. So we're talking of exposing people to a continuous level of something like a medium iPod volume would be one of the more common values that have been set. Now, there are 3 ways in the standards for setting limits. The earliest limits, the oldest limits that were set were from the Wilson Committee report in 1960. They're going back a long way there, where basically it didn't really matter where you were. You could expose people to 70 dB during the day and 60 dB at night, and we just set those limits, and as long as you adhered to those, you were deemed to be compliant. We're going away from that now, and you'll find those limits used much less. And these limits are Oh, I'm sorry, misleading you. These are the residential and office limits here. If you were in an urban area, this is rural area at the top. If you're in an urban area here, then those limits went up to 75 in the day and 65 at night. And hospitals and schools were given lower limits, 60 dB and 50 dB. Interestingly, on schools, although the limit was set at 60 dB, when I've been monitoring schools, they themselves produce far more than 60 dB, so you'd never stand a chance of meeting that. So these limits all came out of the early Wilson Committee report, and they've now largely been superseded by two methods. First one is called the ABC method. This is slightly more complex in that before you start, you have to take background noise levels. And once you've got those at 3 possible periods of time, either daytime, weekends, or night times. Now, if you're not working at night times and you're not working at weekends, you don't have to take those measurements. So let's, for the sake of simplicity, say you're just working during the day, then you'd take the background readings, T1, during the working day, but when you're not working, and then depending on what value you measure, if it's less than 65 dB as the background level, then you're allowed 65 dB as the limit. If it's equal to 65 dB, I should say on here they're rounded, yes, rounded to the nearest 5 dB. So if they're equal to 65 dB, you're allowed 70, and if they're greater than 65 dB, you're allowed 75. So that's trying to take into account the type of environment that people are living in and assess the limit according to that environment. So if they're already used to a lot of noise, then they can be exposed to a bit more. And the other one is quite similar, and it's based on a 5 dB change. So again, you take the background readings in exactly the same way, and you are allowed simply 5 dB more than whatever that background reading was, subject to certain minima. So during the day, the minimum is 65. In the evenings and weekends, it's 55, and at night times, it's 45. So it's quite a simple method, but there is a bottom threshold for it. How do we measure noise for comparison with limits? And there are various different ways of doing that. This one is a full remote monitor, where you would have a microphone in a suitable location near to the sensitive property. It would feed its signal down into a box like this, where the information is digitized on a device like that, goes into a computer where it's processed, so we get building up our LAEQ values in there, and then it uses a cellular router to transmit that information to a remote site and raise alarms should the levels be exceeded. So with communications here, it allows you instant knowledge of when noise levels are getting high. It also reports back all the daily readings so that you can form reports. So you've got a permanent record of the noise that's being generated. And that would be a typical report from a remote monitor. On this top graph here, we're showing the daily LAEQ values. So here was the limit that was set in this particular case, which is a 70 dB limit. We're starting with Monday, Tuesday, Wednesday, Thursday, Friday. Obviously more activity going on Monday, Tuesday and Wednesday. Weekends quieter. But also, when you've got a remote monitor, you can ask for other information to be transmitted to you as well. And this is the LAEQ 1 hour values. So now we're getting a more detailed appreciation of when the noise is generated. And that can be quite useful, because if you take this particular day here, corresponding to that overall level, all we knew from this graph at the top was that the LAEQ value was whatever it was. Here we can say, well, it was really dominated by that peak, and we've got a time against that peak, so we can look at what activity was taking place at that time, and if we feel that that was going to push us over the limit, we can look at some way of mitigating that particular activity. If we find that we are over the limit and we've got to do something about it, then the mitigation options we have are simplest. Let's just use less noisy equipment if we can, or use that equipment in a way that produces less noise. So let's say we're breaking a concrete slab and it's generating noise that goes over the limit. Well, could we put a claw underneath the slab and break it up by lifting it, generate less noise? So if that's by far and away the best approach to mitigating noise. We could time our noisy operations in a more sensitive way. Maybe we talk to the neighbours and say, we've got to do this noisy activity, when can we fit that in? And let them accept that we'll go over the limits, but at their convenience. If neither of those are possible, then we can construct a noise enclosure around the object or activity that's producing noise. That might be a shed, acoustic shed. It might be an acoustic enclosure around a generator or something like that. The important part about that is we're putting the enclosure close to the source of the noise. That's always the better way of handling noise mitigation, is to be close to the source. If we can't do that, then the final and most expensive and the most complicated way of mitigating noise is to put a noise barrier around the site. And there are specialist materials that will both absorb and attenuate sound, heavyweight materials which you can put up on terrace fencing that go around the site. But it's the last option, really. It's the most expensive, most intrusive option. So if we can work down through that list, go for the top ones first.
Right. If you put one of those walls, how many dBs will that knock the noise down?
It's frequency dependent,
Yeah.
but at the best you can get about 30 dB out of it. Yeah. So they claim.
Yeah.
But, all right, just to slightly digress on that, when they do the laboratory tests, of course, what they're doing is showing how much noise gets transmitted through that material. What they don't measure is how much noise has gone over the top.
Yeah.
And so what I've said in the notes is, if you find you need this, go to a noise specialist to advise.
All these building sites now have these plywood walls around them. Presumably that knocks it down 3 dB. So
Yes, that will reflect the sound back, but they won't be as good as these by a good way.
how many dBs would the plywood knock down?
Well, you certainly get your 3 dB. You might get more than that, but again, it's frequency dependent, how high the plywood is as well. So it is very difficult. I'm working on a sound attenuation at the moment where the calculated height that's needed to get the required attenuation is 100 metres. And they're contemplating it. This is a different story. One of the interesting things about these barriers is they're quite available second-hand. So if you do need them, buy them second-hand, sell them second-hand. That's quite a cheap way of using them. Right, because time is pushing on, I better move on to vibration. First of all, define what vibration is. Mechanical oscillation set up from some sort of dynamic forces. In the environment, we've always got vibration around us. There's no way of avoiding it. It's just, do we register it, and do structures around us get affected by it? A vibration is generally characterized by its amplitude, magnitude of vibration, and its frequency. And if we increase levels of vibration, then they can start to cause disturbance to people, which can be a very real disturbance, and they can get to a point where they can harm health. Vibration, white finger. and they can cause structural damage. Vibration is transmitted from its source through the ground, generally, and from what we're interested in anyway, through the ground. So the source might be a railway tunnel, might be you hammering on the ground, any activity which is causing disturbance to the ground. Travels away in body waves through the structure of the soil, and then gets up to the surface and travels along the surface as surface waves. Then reaches a building in the building foundations, shakes the building, and that will be transmitted up to the upper levels of the building, and it can get amplified there. That's one of the important points to note. You can get higher vibration, particularly at the top of a steel-framed office block. The vibration levels can be several times higher at the top than they are at the bottom. And vibrations can then cause things to rattle inside, and it comes out as noise, and people will get confused between what is noise and what is vibration. But the source for what we're talking about now is ground-borne vibration, and that's where it originates. And that can have effects with nearby equipment. So if you're doing works next to anyone using optics, a hospital, research laboratory, anyone in manufacture that needs to look at magnified images, it could interact with that. Electronics manufacturer needs a stable platform, so if you're working next to a building making chips, then they will be affected by it. Anyone using lasers and other research equipment, and hospitals using MRI scanners are very affected by vibration. So if building work's going on near any of these, then vibration could be a particular issue. It can damage buildings. It starts with plaster cracks, cosmetic damage. So here we're talking of quite repairable items of damage, but nevertheless noticeable and alarming to people when it happens. Then we can move on to concrete cracks. These two generally can occur from building works near to other properties. The concrete cracks are more serious in that we are now affecting the structural integrity of the building, and so if those are observed, then we should take action immediately. If the vibration gets larger, then we can get partial collapse or total collapse of a building, but we're talking about earthquakes by the time we get to this level. And if you had an explosion on site, or if you dropped a very heavy object, it's just about possible you could get some of that. But really we're in these two categories here when we're talking of vibration damage to buildings from construction work. Can have a bigger effect on people. Clearly anyone involved with very delicate movements, sudden vibration can be distracting, and well, if you're operating on someone's eyes, it could be more than distracting. So hospitals set very stringent limits on the amount of vibration that they will accept in sensitive areas like operating theatres. It can cause fatigue. If you're constantly exposed to vibration, then you get tired. At night it will cause sleep deprivation, and then in the extreme, when we have very high vibration, we can get physical damage to the nerves and blood capillaries, and get hand-arm vibration syndrome, white finger. Again, we're not so worried about that for neighbouring properties, but workers on site, hand-arm vibration syndrome is a real worry that you need to take into consideration. For vibration limits for buildings, how much vibration can we expose a building to? Again, are covered in BS 5228, part 2, the vibration section, which draws on another standard here. And it bases the vibration on the peak particle velocity. This is the largest velocity that's measured at a point close to where the building works are taking place. The limits are slightly frequency dependent, and they're dependent on the type of building that we're measuring. So if we're looking at a domestic masonry structure, then we get one limit. If it's a steel-framed industrial building, there'll be a different limit that's appropriate. And those limits, which are reproduced in 5228 but actually come originally from BS 7385, are those. And this is saying that the peak particle velocity, so it's the largest velocity that we measure, for a residential property, are for the low frequencies 15 millimetres per second. If we increase in frequency up to 15 hertz, then we can accept more, and eventually by the time we get to 40 hertz characteristic frequency in the vibration, then we could accept 50 millimetres per second. Now in practice it's actually quite hard to work out what the characteristic frequency really is, and so when I've ever done my work, I've tended to set the limit at 15 millimetres per second, and it's not often that that is breached, to be perfectly honest. And these limits here are set for transient vibration. A transient vibration is an event that occurs as a one-off. So it might be a dropped object. By one-off, I mean it could happen several times in a day, but that it's not continuous vibration. If we have a continuous vibration, which might be set up from, let's say, a generator running or concrete pump running or something like that, then all of these limits should be halved. And the reason they should be halved is because we could set up a resonance in the building, and so we've got to take that potential into account. So if we're dealing with continuous vibration, then the limit should be 7.5 millimetres per second.
Where would a pile driver, for example, which is repetitive, that's neither one instant nor is it...
This is impact piling.
Impact piling
would be the transient. That's considered as a transient, yeah. Because it doesn't have the capacity to set up a resonance. The impacts are too far apart.
Okay.
So, the effect from the first impact would be damped out before the second impact comes in. And then for industrial buildings, we've got the 50 millimetres per second transient, 25 millimetres per second for continuous vibration. So those are nice and defined, those limits. Yes.
Those limits apply to the building or to the people?
This is the building. This is the building.
So why is it low for a residential building?
Because steel-framed structures are both more flexible, so they accept more vibration, and they tend to be a stronger type building and are less friable, so a brittle. So if you take a masonry structure with domestic structure with a plaster wall, the walls are very brittle, and so quite small levels of vibration will produce a cosmetic damage. And this is what these limits are actually, is for the onset of cosmetic damage rather than structural damage.
So if you had, say, a very old masonry structure factory, would you apply the residential there?
You'd have to look at it on its merits there. I mean, that's one that doesn't fall into one or the other. My own feeling would be that you would probably use the industrial one, simply because if you did have an old stone warehouse or industrial building, then a cosmetic crack is probably not going to be that noticeable. It would have probably it wouldn't be a fine finish.
Not as sensitive as a residential.
Yes, yes. In practice, all the research that was done to derive these limits showed that buildings in general can take much higher levels of vibration. But because the standards have to give one value, they've tended to be very conservative. So the actual vibration where you really do get into worries is usually much higher than this. You can't be certain, which is why the limits are set quite conservatively. You'll come across some specialist vibration limits as well for properties which don't fall into the general heavy industrial or residential categories. So the first one I've put on here, buildings of great intrinsic value or in a delicate condition or in some way, you really must not damage them. And our British standards give no real help here at all, and the nearest information that gives definitive limits is the German DIN standard, where they talk of peak particle velocity values of down to 3 millimeters per second, which is quite sensitive. MRI scanners have very precisely defined limits, and normal monitoring equipment just won't monitor to see whether you fall inside these frequency dependent acceleration limits. So you have to do something quite specialist if you're going to be operating or doing works that create vibration near an MRI scanner. And they tend to be acceleration based. Optical instruments tend to have velocity limits, which are again frequency dependent, and these different limit curves here depend on the magnification of the instrument you're using. So if you're using a times 10, or whatever that is, 40 is it, then you can accept much more vibration than if you're using a times 1000 instrument there. So those are the specialist vibration limits for equipment and for buildings. When we get to human response to vibration, it becomes an order more complicated. And it's because the disturbance we feel from vibration depends on so many factors. Depends on our age, our health, where the vibration is coming from, which direction it's coming in, whether we're sitting, standing, lying down, what frequency the vibration is, how long we've been exposed to it, how big it is. All of these things can affect how we're disturbed by vibration. And the latest research, and now the standards are beginning to adopt it, to come up with an exposure value, a vibration exposure value. So it accumulates all the vibration you feel in the course of a day or a night, and you end up with a single value at the end of it, the vibration dose value, which is how much exposure to vibration you've had, and then we can look at that value against a limit to say, yes, you've probably been disturbed by that vibration, or you've definitely been disturbed by it, or no, it's unlikely you would be. And because we feel vibration differently at different frequencies, we have a weighting factor like the A weighting for noise, but a vibration weighting factor for how our bodies perceive vibration as opposed to how an instrument receives it. And that weighting factor is different for when we're lying down, standing up, and so it becomes a nightmare to deal with. Fortunately, the standards say, well, that's too complicated. We'll just consider one of the weighting factors. And the weighting factor that they prescribe is called the WM weighting factor. Again, instrumentation that you use for measuring vibration has all this built in. So this is just background knowledge, and you don't need to know it. I thought I'd put in what the vibration dose value was, because there's a nice little elegant formula there, which again you won't have to worry about because you won't be doing that integration. But it's been defined as the time integral of the fourth power of acceleration to the 0.25, power 0.25. So you end up with a unit of exposure of meters seconds to the minus 1.75, which I think is just wonderful. Never have I seen a unit like that before. However, you don't need to worry about the units, you don't need to worry about the formula, because the instrumentation just comes up with these vibration dose values, and all you do is say, are we above the limit or are we below it? And the important thing is that it's an exposure value. So you can accept one or two large bumps in the day, and you might just be under the limit, or it might be you've got continuous low-level exposure and you'd come to the same limit. So it's and apparently that's the way that we are disturbed by vibration equally by one or two big events or continuous lower events. The guidelines for vibration, the earliest guidelines are still based on PPVs, peak particle velocities, because in the early days instruments could only measure peak particle velocities. And all that's telling you are the levels of vibration velocity where you're likely to feel it or maybe not feel it or maybe slightly disturbed by it. These guidelines are generally out of date now, and you won't see those so much. These are the guideline values which are taking their place, and these are on the vibration dose value, and we can see here that if you are in a residential building in a 16-hour day, then as long as the vibration dose value doesn't get above 0.4, you're not likely to get adverse comments. And so local authorities would generally accept 0.4 as the level of vibration dose value that you can expose your neighbours to. Once you get up to 0.8, then you possibly will get some comments. Once you get to 1.6, then you're almost certain to get some. At night, those values are essentially halved, and these refer to residential buildings. If it's offices and workshops that are adjacent to your works, then you can take these values and multiply them by for offices by 2 and workshops by 4. So in theory, you could have 6.4 is, well, no, if we go down to where you wouldn't cause disturbance in a workshop during the day, then you would that would be a value of 1.6 there as your vibration dose value limit. If you're working next to a hospital, then there's a Department of Health technical memorandum which covers vibration levels, and that's based purely on acceleration. And the acceleration limit for a operating theatre is 0.005 meters per second squared. That is 0.00005 G. That is completely unrealistic. You could not pick up an instrument from the table and without exceeding that limit. So why it's set, I don't know. But anyway, there they are.
Is there any legislation to sort of back up
Yes,
that?
there is. There's teeth to this. It's astonishing, but there we are. That's what it is. And they insist on WG weighting as well in there. But I mention it because it's there, but I can't support it. If you want to measure vibration, there's various ways of doing it. Handheld devices. This particular one here does sound and vibration, and I brought one with me today, so at lunchtime if anyone wants to have a look and see how they work, I can show you that. That one's for site monitoring, so you get a readout on site to give you values of vibration dose value or peak particle velocity, and if you'd have to go and take those values and jot them down, or you can get them transmitted remotely, or you can go for complete continuous monitoring with remote access to so the data is sent remotely.
But what's the monitoring equipment? What picks up the amount of vibration?
In this one here, the sensor is fixed to the wall down in here.
Mm-hmm.
So it's a triaxial accelerometer measuring 3 axes at the same time. Well, no, you would. That's in a weatherproof box there, and then it'd be screwed to the wall. It has to be bonded.
The sensor is like a pendulum with a...
No, it's actually a piezoelectric, has an inertial mass and a piezoelectric sensor underneath. So any vibration causes a charge which generates an electrical signal, and that's what's measured.
Right.
So again, I brought one of those with me. Have a look at it at lunchtime and see what that's involved. So with both of these, there would be a wire coming out of here to a sensor, which you'd fix somewhere. And similarly with this one of these cables here would go out to the sensor. So it's sensor and then things which do the measuring and transmitting the data.
It's a bit like a gramophone pickup.
No.
Okay. Right.
I will. I'll show you at lunchtime, and you see how that. Oh. Right. So here would be a typical report. Have I gone two? No, I haven't gone one. That's a typical VDV report, vibration dose value report, and this is taken at 1 hourly steps. So we start our day here, and you can only ever accumulate with the vibration dose value. It's an exposure value, so it only ever gets bigger until the end of your period. So if our limit was 0.4 here, then gradually through the day we built up till we got to 2300 hours, which was defined as the end of the day, and that's the largest exposure value that we reached on that day. I like to do it this way, as showing it as a growing value rather than as a single value, because times when we get big jumps, we can identify what equipment we were using and what's contributing to the eventual vibration dose value. And then it drops down as we reset for the night period. The night period accumulates very little vibration because people weren't working at night, and then we start the next day period again, and so it goes on. And weekends are quieter. They're obviously doing a little bit of work on Saturday there and no work on the Sunday. And there's two lines on here because they were from two different monitors. So one was closer to the works, the other was further away. But in both cases, they were nowhere near the limit. There's on a logarithmic axis here. So there would be no justification for anyone saying we were disturbed by the vibration. This is from 5 separate sensors. This is the peak particle velocity. Remember I said we'd generally take the limits at 15 millimetres per second. Well, in this case, we got to about 2.5 millimetres at the worst time during the week. So again, there would be no justifiable claim from anyone that there was any vibration damage when we got values of this sort of level. And that was it. I think I might have overrun my time.
Can I ask you a question, if you don't
Yes.
mind? A typical day for you, right? We've got a site in Swansea Marina where they are going to be piling it. I'm a party wall surveyor. Next to it is a fish market, chandlery and a restaurant.
Yes.
Industrial buildings. I've suggested that piling should have some type of monitoring, what's been considered, and I'm being told that I'm being completely over the top. Leave it to the engineers, why are you getting involved, blah, 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 blah. So, on a job like that, right, how would you be approached? Would you be approached by the engineers? Would you be approached by the contractor? Or would it maybe come via the environmental health department of a local authority? How does it work?
I can tell you who wouldn't approach us, and that's the piling contractors.
Yes.
They don't tend to like this being done.
Yeah.
Although
Yeah.
that's a bit unfair. Local authorities will be very keen.
Yes.
Is it impact piling?
Yes.
Yes, they would be very keen to prevent.
They're the freeholder of buildings next door as well.
Are they? Well, I would have thought they would have been
Yeah.
quite anxious about that. But I've been approached by almost everyone,
Yeah.
really, who thinks, oh, this might be an issue. Usually it starts when the plans become public and people realise what's going to happen near to them, and they become worried and start making inquiries. Well, how do we know that you're not going to damage our building?
Yes.
And so that, quite often, if the local authority doesn't kick it off, that's something which will kick it off there. But realistically, it ought to be seen as a benefit to both sides,
Yeah.
because those that you're trying to protect need some sort of reassurance. they're understandably frightened when they feel and hear vibration. You know, if I can feel it, what's it doing to my property? That's quite understandable. But it's also quite useful for the contractor doing the work as well, because they end up with a permanent set of records for which, in future, if someone comes back and says, look, my chimney fell off last winter, and I think it was weakened by the work you did. And if you've got the records to say, no, we didn't, this is the level and this is supported by national standards, then you've got a pretty watertight case there. So it's not a one-sided thing, the monitoring. It gives protection to both sides.
For, say, an 8-week piling period, what would the charges be for a specialist like yourself to come to site, set up, remotely monitor so that this data is available?
Usually the setup and decommissioning, because there's a fairly complicated installation which has got to be done, and that works out at about £1,500. And then the monitoring, I don't think of it so much as a monitoring as a sort of vibration management, because there's all sorts of the mitigation goes in it. But it's about £300 a week after that. But basically what you're getting then are all the reports and all the mitigation advice in with that.
Right.
So, but that's typically the sort
of course.
of cost.
Right. Okay. All right. Thank you.
Yes.
Those limits for the hospital, are they actually, is that vibration actually acceptable to a person?
No, not really.
So do hospitals monitor vibration with machines, instruments?
No.
To check? No?
I mean, I've been in operating theatres where they wanted to know whether this was suitable or not. They'd been used in an operating theatre for a very long time. I couldn't walk across the floor without exceeding the limits. I don't know how those limits were derived. It's just bizarre. They're almost difficult to measure with standard instrumentation.
And those normal limits for the buildings, are they perceptible to people?
Oh yes. Oh yes, yes. At 15 millimetres per second, which is where we might start getting cosmetic damage,
Yeah.
you would be thinking about getting out of your chair and leaving. It's surprising what buildings actually can withstand. It's, but we have to be careful, because buildings don't feel vibration as we feel them, and using velocity as the measure is a very approximate way of doing it anyway. Buildings don't really respond to a velocity level. It's much more complicated than that. But that's the closest that we can get to. But the closest we can get to for people is we respond to acceleration. Now, both are actually measures of vibration, and they are interrelated. But you can't take a velocity level and equate it straight to the acceleration level and say, oh, well, if that's what it was felt on the building wall, how would we feel that? You'd have to assess that same vibration in a different way. And so sometimes you can get damage to a building which you would scarcely feel as a person, and sometimes the other way around. Sometimes you feel vibration quite dramatically and it's not doing any damage to the wall. So we do have to be a bit careful when relating one to the other, which is why they are kept quite separate when we're setting limits. It's a vibration dose value and a peak particle velocity for buildings.
Any other questions? Thanks, Brian. That's great.